And welcome back to Section 3 of our helical pile training and certification class. In this section, we're going to cover some basic geotechnical information, design criteria, and go over how to calculate, go from load capacity to torque requirement for a particular type of pile. So a subsurface exploration, or a lot of you know it as a geotechnical report, it's very important to get and perform one of these tests whenever economically feasible on any project that a helical pile foundation is used. If you go to IBC, geotechnical investigation is one of the criteria for helical pile installations. However, it is at the owner's behest and at the building department's behest if they require this on lightly loaded or residential projects. So sometimes you won't have these available on residential projects or residential repair type projects, but maybe on a new construction application. Certainly, we highly recommend it for any commercial work that you may be doing. So during this subsurface exploration, the driller will be taking down information, and also the geotech engineer will be doing lab tests that will provide the helical design engineer with certain parameters to be able to specify the proper helix size and shaft size and depth for the project. The key component to this report is the boring log. There's a lot of great information that's contained within it after the drilling is done. So if you look on the right side, this is a typical boring log, what it looks like. It'll have the location, maybe the day that the bore was performed, along with the temperature, the start time, the end time, and any other relevant information, including soil classification, water table depth, and blow counts. And they'll show the whole soil classification throughout the whole boring log. So this will show where bedrock is, and it'll also indicate drillers' observations during the drilling process. This will be key to find out if there's any obstructions, cobble, debris, material that exists at the site that may cause issues with helical pile installation. One of the key factors within this, or sampling methods within this, is called the split spoon sampler test, or the SPT, standard penetration test. So this involves putting a sampler in the ground that will split in half, and a hole is drilled at selected intervals, a 4-inch diameter hole typically with a hollow drill stem auger. The sampler is dropped in at specified depths, and it is hammered into the ground with a calibrated hammer. So typically it's dropped, a 130-pound hammer dropped 30 inches in the air onto this sampler multiple times until you reach an 18-inch overall distance of travel for that sampler. So every time the hammer comes down, that blow count is recorded. The final 12 inches of movement, all of those blows are added up, and that's what's called the blow count, or the N value. Generally, the higher the N value is, the denser the soil material is that you're going into. So this is something that the designer will use to empirically relate the capacity of the soil to then properly size the helical pile bearing plates. So it's really critical information that we look at as helical pile design professionals in indicating how deep the pile will go. Typically for a residential foundation load, you're going to see a blow count requirement somewhere in the 20 to 30 blow count to gain the capacity you're looking for those types of loads. And then it can vary depending on what size helixes you end up designing for the project. But using the normal size helixes, that's kind of the range you're looking for. Once you get beyond 50 blows per foot, you can have helical pile refusal during installation. So it's so dense that the pile reaches its maximum torque and it can no longer be driven. Also, sometimes if you have a very weak soil that has maybe in the single-digit blow count, and then all of a sudden it gets into a really stiff, hard material or a bedrock that's greater than 50 blow count, the pile can spin out or cavitate, stop advancement, and just rotate on that material. And then you'll have to adjust the down pressure to get it to rebite into the soil before it'll continue to thread in. So soil is classified generally by particle size, from smallest particle to largest. So if you go from the left to right, you have clays as the smallest, then up to silts, sands, gravels, cobbles, and boulders. And you can have a mixture of all of these soils together. And when the soils are mixed, the designer will run calculations as if the particles are cohesive in nature, meaning that they stick together, or cohesionless, like your sands and gravels that act as separate particles. The designer will run the calculations both ways to see which one is the smaller of the two results. This is part of the initial design process after the soil report is done. Again, this is going to be for the design engineers out there, not necessarily information that you need to remember as an installer. Corrosion is really a key factor when it comes to soils and how it affects the pile longevity and capacity. So the rusting process is a chemical reaction that decreases the life of the helical pile. Anytime you have a pile in soil or in air, that rusting process will occur as long as there's free oxygen available. So typically your highest corrosion area is between ground level and maybe 6 to 8 feet in the ground, where you have fill material and free oxygen available. That's your highest area for corrosion. The first type of corrosion protection is called corrosion allowance. And this is the thickness of the steel. It will have a sacrificial element to it. So with our smaller piles, we've built a sacrificial corrosion allowance within that steel itself, so that for an average soils, it'll corrode enough in 50 years that you're still able to get its maximum service life. So its maximum load capacity. So on average, your smaller piles are going to average 50-year service life, bare steel, in mildly corrosive soils. So AC358 is a independent accreditation process for the helical pile system, and they've established some criteria for corrosion loss. And what it says is that a bare steel pile will lose approximately 0.036 inch of wall thickness in a 50-year span. After 50 years, the Piertech 2 7/8 pile will have an allowable capacity around 50 kips. So you can design that pile to 50 kips. So that allowable capacity is also known as the working load capacity. So you can design it for that 50 kips after and be 50 years service life. So if you wanted to get more service life off of it, you'd start eating into your allowable capacity of that pile. So hot tip galvanizing is something that adds additional service life as well. So hot tip galvanizing is a chemical process where the zinc melds with the steel and chemically changes the outer diameter to create a protective barrier. And generally it's in the 4 to 7 mils of thickness. This type of protection is great because it works very well when you're installing into the ground and is does not polish off while it's being installed into the ground, and it adds typically in that 25 years plus in the average soil conditions. Some soil conditions it'll add quite a bit more, and some it'll be quite a bit less. Other protective coatings are out there. So let's say you're putting in a marine pile into a lake or near brackish water. There are epoxy coatings and polyurethane coatings that you can add onto the pile after the fact that are have higher abrasive resistance when you're going into the ground. So they're able to stay on there a little bit better. The great thing about these coatings is they encapsulate the steel and prevent it from corroding. So if you've got these in those applications where your pile is sticking out of the ground, you may have some maintenance over the years to reapply coats where it's worn away, but overall it's going to really increase the length of your pile in those types of applications. The last option is called cathodic protection. And cathodic protection would be where you either add galvanic anodes, like zinc anodes, similar to a outboard motor of a boat. So those anodes will corrode before the steel itself will corrode. And typically those galvanic anodes are added to a bare steel pile or an epoxy coated type pile versus a galvanized pile. And then the second is an impressed current. So that would be typically done on piles that are in the ground and are exposed, have a very large exposure surface area. So very large piles potentially, or areas that have maybe welding is being done, or there's some sort of DC current in the ground. So that's when you would potentially impress a current on those piles. So what some of the triggers that for more in-depth study would be really low resistivity. And resistivity is measured in the ground by, similar to resistance within a wire, you want to make sure you have a higher resistivity that'll lower the corrosion rate. If your resistivity is very low, it speeds up the corrosion rate. Also a pH. You want to have a stable pH ground. That'll help prevent the pile from corroding faster. So if it's unstable, you're below the 5 to 6 range, or you're above the 10 range on the pH level, you could have a high potential of corrosion or a higher potential of corrosion. And then the sulfate content. If you have a high sulfate content, that also will cause corrosion. Similar with a chloride content in the soil. High chloride content will then increase that. So these are all, or water content that fluctuates. So if you have a groundwater table that's relatively high and it fluctuates, it's going to have a much higher corrosion rate on the pile. So it's good to have galvanized piles in there, or maybe even encapsulate that pier with a concrete sleeve near the surface where you have that fluctuating groundwater level. All these are very important for looking at for more in-depth studies. And if you get into this, you'll want to make sure the geotech engineer understands this aspect of it, and you may have to hire a special corrosion engineer for a project that's in one of these areas that is very susceptible. All right, so I want to get into design and specification for commercial projects and what kind of things you're going to be seeing for submittals, and what you're going to be seeing required for the drawings, working drawings for the project. So the first part of the submittal is you're going to see that piles will need to be installed by an authorized installation contractor. So you want to make sure they're authorized by the manufacturer of the pile they're putting in. So that's what you're doing here today. Some projects may even require additional experience levels. So they'll want you to have experience on projects of similar size. If you don't have that and you're new to getting started, a lot of times Piertech can be part of that experience, and we may be able to send somebody out to be part of the project with you at the start, to lend that experience side that's required in the submittals. Next, you want to make sure you have the pile design performed by a registered engineer in the state of the work that is being performed. So if you're in Colorado and you need a project done, you want to make sure you have a Colorado licensed engineer performing the work. If you aren't already linked up with somebody that's familiar with helical piers, we have a network of engineers we work with that we can refer you to that can perform that design submittal work that may be required on your projects. So please get into contact with your salesman if you have that requirement. Next, you'll want to submit a QA/QC plan. So you'll want to make sure that you're doing something to verify the material is what you ordered when it comes to the site. That includes measuring dimensions and lengths and helix sizes and all that to make sure that the material is what it is. And you want to be able to create that plan on the front end, submit it to the owner or the owner's representative so that they know how you're going to make sure that you're putting in the right material for that project. Next, potentially a load test program may be required in the specifications. If they're required, you want to put together what your load test program will be. And most specifications spell that out, what they want the test to be, how many tests they want, and what type of test they want. So you'll put that information in the load test program along with the equipment that you plan on using and any sort of calibration certificates for that load test equipment. I talked about that in an earlier section, so if you need a refresher, go back to that first section, section 1, to refresh on that load test process. We can also get a little bit more involved with that with you when that comes up. Next is equipment calibration. So sometimes they'll require that the torque drive or the torque motor is, our torque monitor is calibrated for the project. And that calibration, they'll want that done within the last year of the project. So the best method is that IntelliTorque real torque monitor I talked about for calibrating this, for meeting the submittal requirement. So if you have that monitor, it comes with the calibration, you can submit that and you'll be good to go. If you have the pressure gauge system, you may want to consider getting one of the real torque IntelliTorque monitors to satisfy this requirement. Next would be stamped material cut sheets. So we'll provide cut sheets for the material we're doing, but they'll want them stamped for the state of work. That's part of the third-party engineers' scope of work. So they will then review those material cut sheets for this project along with their calculations and stamp that for the use on this project. And then we've got pile installation logs. So we showed an example of a pile installation log earlier. They'll want that log example in your submittal. And then for closeout submittals, you'll have to supply these pile installation logs for every pier that you put in on the job. This could be done the day that you do it or at the end of the project, depending on what the specifications require. Next, we have special inspections. Special inspections will involve either the owner or the owner's representative hiring out a geotechnical firm or somebody familiar with inspecting the helical piles that will go out and watch the torque gauges and write down the pressures and make sure that the pile is being installed per the specifications. And they'll also do a QA QC on the piles as well by measuring and making sure the pile material is what it shows on the working drawings. And they'll also verify depth of installation, the tolerances, the cutoff elevation, all of that key elements for installation. That's what the purpose of those special inspections are. Typically, you won't see a special inspection requirement for residential work, decks, foundation repair. Certain municipalities will require that, so make sure you check on that before you start a project, so it doesn't hold up your permitting or slow down your project there. If you're involved with it and you're dealing with an inspector or a building official on a residential project and they're really wanting the special inspection, we can talk them through that. Because you're being certified as an installer and you're using calibrated equipment, we should be able to get an exception for the special inspection on smaller, lightweight residential projects. Next is what the working drawing requirements are. So these will be the documents that you work off and you use to install the piers, locate, all of that. So first off, they're going to require the helical pile number, so all the piles to be numbered, show the location, and pattern by assigned identification number, so where those are on the specific plans. Then the design load, what the working load requirement is for that pile that's being installed. Sometimes that will be the same for every pile on a project, and sometimes every project will have a different design load requirement. The third would be the type and size of the central steel shaft. So if it's a round shaft or a square shaft, and if it's 2 7/8 or 1.5 inches, that will be specified on the working drawings. Then you have the helix configuration. We talked about that earlier. So you've got your single helix leads, double leads, triple leads. So that configuration, the number and the size of those helix blades will be written on the working drawings. Next, you have the minimum effective installation torque. So this is your target torque on the project. And you'll want to make sure that you meet or exceed this torque before you move on and stop that pile installation. So that will be something that's written on the working drawings. And then you have minimum overall length. So if they want you to meet a minimum depth of embedment, they'll say, we want you to meet 25-foot embedment. So you want to make sure that that's on the working drawings for every pile that you need to install. And then next you have installation or inclination of helical pile. Most piles will be installed vertical or plumb, but some piles will be installed at an angle. We call it a batter. So that angle will be required for piles that are taking up lateral loads, shear loads within a structure. And typically, sometimes you can see that angle anywhere from 5 degrees to 45 degrees, depending on the project requirements. If you're doing a pile at an angle, you can start the pile vertical, and then once you get it embedded a little bit into the ground, you can start pulling it towards the angle you're installing. So you start it out vertical, get it in 6 inches or so, and then start moving it out at an angle, so that once it's in there and you've got the right location, that it's not going to walk on you during the installation. And then you've got cutoff elevation. What elevation is the pile need to be cut off? How far up into the concrete pile cap or grade beam do they want that pile cut off? And that elevation will be part of the working drawings. Also, the attachment. How is the pile attached to the structure relative to the grade beam, column pad, pier cap, etc.? So that'll be another component. One other thing I didn't put on here was the tolerance. That's also going to be specified on the drawings. How far off of location can you be? It's very important to have an understanding of that before you go do the project, or else you could get installing a bunch of piles and have to go back and relocate and move some of those. So make sure you really plan this out before you start your project. All right, next we have material requirements. Sometimes a project may require an independent code council report, evaluation service report. called an ICC-ES report. This is an independent third-party accreditation company that certifies a building product for use in certain applications. We do have a ICC product for one of our pile sizes, and we're continuing to grow onto that as we advance. So please let your salesperson know if the project does require a ICC report, and we can get that information to you and get that right product quoted. Next, we have sizing helical bearing plates from a design standpoint. You know, how does a pile really function once it's in the ground? How does it transfer load? Well, there's really two methods it's transferring the load into the soil. One is by plate end bearing. So that's the right side picture here, the individual bearing equation. So the load gets transferred down through the top of the pile here, shown by the arrow. And then there's some side friction with the shaft, very small amount that's being resisted along the shaft. And as it goes down, the load transfers into each plate of the pile and bears into that soil layer. So this is an individual plate bearing. So very minimal skin friction, mainly bearing of the plate into the soil. The other way is called cylindrical shear, and this is the left side. So with cylindrical shear, you have the load coming down here in the area, same as before, and then the shaft in friction with the soil. And then when you get down here, the blades are spaced close enough together to where the soil creates a plug within that multiple flight pile. And that plug is within shear or skin friction with the soil surrounding it. So those are the two different ways that the pile capacity can be calculated, and the helical pile design engineer will run those calculations for both equations and take the lowest value of each one. So for those of you that want to get into this and understand this a little bit better, you can go to starting around page 24 of our engineering manual. You can read all about these equations and learn more about how these loads transfer in the pile. So there's other design considerations that go into designing a helical pile system. These normally play a very small role and are seen very infrequently on projects, but have to be considered. So the first one, shaft buckling. Shaft buckling can occur when a pile is in air or in a fluid soil. And a fluid soil would be one that has a blow count value of 0, meaning that when they drop the hammer down or set the hammer on that soil, it drops the 12 inches without any effort. It can't even support the weight of that 130-pound hammer. So that would be considered a fluid soil. If a pile is within that soil, it's acting like a column, and it's not braced laterally from buckling. So buckling can become a concern. So anytime you see that in a soil report, or your torque values essentially are nothing as you're going into the ground, you may have buckling concerns of that pile. So it's very important to get a geotech investigation and get a structural engineer involved in those types of soils. The solution to that problem would be increasing the pile diameter or potentially casing around the pile after installation. Both of these are acceptable methods to prevent buckling. Next, you have shaft adhesion. That is typically negligible on a small shaft diameter pier, but when you get into the bigger Hercules pier, you do get some skin friction out of the pile that adds to capacity. Next, you have pile deflection. Pile deflection is usually doesn't control on residential projects, commercial projects. Sometimes it starts to become more of a control. And then really when you get into sensitive equipment that you need very minimal amounts of deflection, that has to be accounted for in the design. Next, you have down drag. So down drag can occur when you have a very large layer of fill and it starts to collapse over time and add additional skin friction on the pile. So it's quite negligible with the smaller diameter helicals. Then we have group effect. Group effect occurs when piles are spaced close apart, so typically less than 3 feet. You start to get the piles bearing on the same material. And when that happens, the capacity is reduced because they're sharing the same soil. So as a general rule, you want to keep a 3-foot minimum spacing for a small diameter helical, something 12 inches or under. And then if you get closer than that, you want to put the piles at a slight batter so that the helixes are at least that far apart. That way you don't have to take or reduce the soil capacity. That's something to keep in mind when you get into some higher loads where you have to put piles close together. Typically column pads are the main areas where this comes into play. Next you have pile load testing. We talked about that before. Here's an example of a very light loaded pile test, just two reaction anchors and a cylinder being loaded up. This is a verification method for verifying that you've reached the capacity you're looking for. Then you have expansive soils. Those are soils that tend to shrink when it dries and expand when it gets wet. So the expansive soils can cause a lot of problems with foundations if you have the helical bearing plates within that expansive soil. So you want to make sure you install those well below any expansive soil layers. Then you've got lateral loads. A small, slender helical pile will only resist maybe 500 to 1,500 pounds of lateral load, depending on the soil condition. So if you have to have higher lateral load requirements, you may have to increase the shaft diameter, encase it in concrete, or put the piles in at a batter to take up that lateral load. Again, helical piles generally are designed just for axial loads and not for lateral loads. But we know there are some light loaded applications like decks and small out structures that will require some lateral load. So you want to make sure you account for that in the design. And lastly, probably most important to make the project feasible is economics. So if you take all of these into account during your design, you can be very economical. Sometimes it looks expensive to have a soil report done, but it'll make the project cost less in the long run. Same thing goes with load testing. Usually the load testing will actually save you money on the project from an over-designed pile system. All right, the next thing I want to cover is the capacity to torque equation. Make sure you take good notes here and write down any information that you see, because this is going to be on the quiz for this section. So this is going to be very important. The capacity to torque relationship is an empirical formula that has been derived from hundreds of load tests that have been done on helical piers all across the world. So it relates the ultimate capacity to the helical pile directly to the final installation torque required to insert that pile to a given depth. So this equation can be found in 4.5 of our engineering manual, and we've got about a 2.5-page write-up that goes more in depth about how the formula was developed. So there's two ways of looking at the equation. The first one is, well, before I get into that, I want to get into the terms that are used in the equation. The first one is called QU, and that's the ultimate capacity. We already talked about ultimate capacity earlier. That's the working load times the safety factor. So the working load times 2 for most helical piles. And then you have the K factor, which is also known as the capacity to torque ratio. The capacity to torque ratio is specific to the shaft size you're installing. I'll show you here those on the next slide. And then lastly, you have T, which is the final installation torque. And that'll be something that you collect in the field as you're installing. So the first version of this equation here on that I'm circling right here on the left side is going to be the main way that you're going to be using, or the main equation that you'll be using as you go about and do projects. So with this equation, you'll have the ultimate capacity that you've calculated by doubling the working load, and then you'll divide that by the shaft K factor, or the capacity to torque ratio as we call it. So that's the equation. You'll take your ultimate, divide it by K, and it'll give you your final installation torque. You can also look at the equation as if you're going out in the field and probing the soil and doing a test to figure out what the capacity of the soil is. So at a given depth, you can take a torque reading, and then you can multiply it by the K factor for that pile. And that'll give you the load capacity at that depth. So this is very handy if you don't have a soil report and you want to go ahead and test out a soil site condition before doing a project. All right, so the K factor, there's some common K factors for 3.5 inch and under shaft diameters. So for the 1.5 inch and 1 3/4, the K factor is 7. So it's typically a 7-to-1 relationship. Or sorry, 10. A 10-to-1 relationship for the K factor on 1.5 and 1 3/4. And for the 2 7/8, the K factor is 9. So for every 1,000 foot-pounds of torque, you have 9,000 pounds of ultimate load capacity. And then you go down to the 3.5, the K factor gets down to 7. So it's for every 1,000 foot-pounds of torque, you have 7,000 pounds of ultimate capacity. As you notice here, as the shaft diameter gets bigger, the K factor goes down. Well, the reason for this is the surface area in contact with the soil becomes much larger the bigger you get. So you want to take out that false sense of torque from the shaft diameter. You want to really base it off of what the helixes experience itself. So that's why we're reducing the K factor as we get bigger in the shaft diameters. The K factor is less reliable, and based off the shaft size, it starts to become more specific on the soil condition and the helix blade geometry when you get into the larger pier shafts, the 4.5 inch and above. So typically either higher safety factors are used, or you go to a load test program to verify what that site-specific K factor is. So as an example, 7-inch OD shaft typically has a K factor in the range of 3 to 4. So for every 1,000 foot-pounds of torque, you have 3,000 pounds of ultimate load. So as an example, let's say you put 10,000 foot-pounds of torque on both an 1.5 inch square shaft and a 7-inch OD helical pile. So with 10,000 foot-pounds on a 1.5 inch, you have 100,000 pounds of ultimate load. But if you put 10,000 on a 7-inch, you're only going to have 30 to 40,000 pounds of ultimate load. So it takes quite a bit of more torque on a 7-inch to get to the same kind of load capacity. I hope that explains it. We can, if you have questions on this, we can write them down and we'll discuss it a little bit further in the Q&A session. All right, let's do a couple examples, some real-world examples. So with this first example, we are underpinning a residential foundation. So we're repairing it. And we've determined that there's a working load requirement of 25,000 pounds. So go ahead and write this down with me. So what we want you to determine is what is the minimum required installation torque. So I'm going to go through the step-by-step process, and this will be the same regardless of if you're doing a residential repair or you're doing a commercial construction. Step 1, you want to calculate the ultimate load. So think back to the previous section on how to calculate ultimate load. So ultimate load is simply the working load times the factor of safety, which is typically 2 for the helical pier. So ultimate load equals the working load times 2. So we take 25,000 pounds and we multiply it by 2. That equals 50,000 pounds. So we've now determined the ultimate load needs to be 50,000 pounds. We go to step 2. Step 2 is determine what is the required pile. So for this step, you'll have to go back to the previous section and understand what the maximum load capacities are for the different pile types, and also what applications fit them best. As you recall, you typically want to use round shaft for compression applications and square shaft for tension. So for a residential underpinning where you're supporting the foundation, that's a compression application. So you want to choose the round shaft material. Then you look between the 2 7/8 round shaft and the 3.5 inch round shaft. So the 2 7/8 has an ultimate load capacity of up to 100 kips, and the 3.5 has an ultimate load of up to 120 kips. So we've got an ultimate load requirement of 50 kips. That means that we can use either the 2 7/8 or the 3.5 inch. So you'd want to choose the 2 7/8 as it's going to be the least costly option. All right, so we're choosing round for compression application and 2 7/8 because it's less than 100 kips. All right, next we want to determine what the K factor is for the 2 7/8 pile. So for this, you determine the shaft size is 2 7/8. You go back to the previous slide and determine what that K factor is. That K factor is 9 for the 2 7/8 pile. All right, so the last step is calculate the torque. So if you remember from the equation previously, to calculate torque, you take the ultimate load, QU, and divide it by the K factor. So the ultimate load was 50,000 pounds for this project, and the K factor is 9. So 50,000 divided by 9 is approximately 5,600 foot-pounds. So if you're in the scenario and you've calculated 55, that will be difficult to precisely read on your pressure gauges, so you can always round that to 56, round it up to 5,600 in that scenario. All right, so we've taken our first run at going from working load to installation torque. I hope that everyone has a good understanding of that. For those who don't, we're going to go through one more example. And the same question are givens here. We're going to have the working load of 40,000 pounds for a tieback application. Question I have for you is, what is the minimum required installation torque? Going to go through our 4 steps again. First step being calculate the ultimate load. I'm going to give you a second to work this out. All right, so ultimate load is the working load times 2. Remember, 2 is the typical safety factor for the 2 7, or for the small diameter helical pier. So we've got our working load is 40,000 pounds times 2. equals 80,000 pounds. So 80,000 pounds is our maximum, absolute maximum ultimate load requirement for this project. Next, determine the required shaft size. I'm going to give you a second to figure this out. All right, for those of you who chose square shaft, you're correct. We choose square shaft because it's a tension application. We're pulling on the pile. And we discussed in our previous section what the advantages are of the square shaft for a tieback application. Next, we want to choose either 1.5" or 1 3/4". Now, the 1.5" has an ultimate load capacity of 80,000 pounds. The 1 3/4 has an ultimate load capacity of 100,000 pounds. You could choose either one, but I would recommend choosing 1 3/4 for this. And the reason for that is you never want to design the pile to its absolute maximum load capacity. I discussed that a little bit in section 1, but you don't want to overload a pile to the point where you don't have additional capacity in case you need to get through a hard layer of soil, and you don't have any additional torque in your pile to do that. So I would bump it up to the 1 3/4 shaft. If you chose 1.5", don't be upset with yourself. It's completely understandable of why you would choose that, and you'll learn over time that you want to be cautious when choosing the pile and keeping it about 20% or so away from its maximum ultimate capacity. Next, you want to determine the K factor. So I'll give you a second while you determine that. All right, so we know from a few slides back that the 1.5" and 1 3/4 both have the same K factor, and that is 10. So every 1,000 foot-pounds equals 10,000 pounds of ultimate load. Step 4, minimum torque. So now you can calculate your minimum torque. I'll give you a couple seconds to do that. All right, so minimum torque is simply the ultimate load divided by the K factor. So QU again is the ultimate load, and you divide it by the K factor. Our ultimate load for this project is 80,000 pounds, we determined from step 1, and the K factor from step 3 is 10. 80,000 divided by 10 is 8,000 foot-pounds of torque. That is now our minimum installation torque requirement for this project. So write these steps down. You're going to have to go through these same steps on the quiz. All right, next I want to introduce the pressure gauges. So in the previous couple examples, we determined what the minimum required installation torque is. And the units for that are foot-pounds of torque. If you are using pressure gauges, your units are PSI. So we have to have a conversion to go from torque to pressure, or from pressure to torque. So this is where this step comes in. This is called the inline pressure relief. This measures the differential pressure drop across the drive head using two gauges. The forward gauge, that's this gauge here, furthest from the valve, that's the forward gauge, and the back pressure gauge, which is the gauge closest to the valve. So when you're spinning in the clockwise direction, the pile into the ground, your forward pressure gauge should always be reading higher than your back pressure gauge. If it doesn't, you most likely have your lines reversed. So go ahead and switch those around if that's the case. Next, you calculate the differential pressure by taking the forward pressure reading and subtracting out the back pressure. So an example would be if you have a forward pressure of 1,000 psi and a back pressure of 200 psi, your differential would be 1,000 minus 200, which is 800 psi. So now you know how to calculate differential pressure. Now I want to show you the chart that relates pressure to torque. So this is an example chart for an old model drive, the RS-12K. It has the pressure on the left side on the first column. This is the differential pressure. So this is the pressure drop across the drive. Then it has torque, and the torque is in foot-pounds. These two columns relate directly with one another. They can be directly correlated. So 1,000 psi of pressure, differential pressure, equals 4335 foot-pounds of torque. The same goes for 8,677 foot-pounds of torque equals 2,000 psi of pressure. So those two relate directly with one another. And then for sizing purposes for your drive head and determining how fast your drive head will go, we use flow rate, and this is the speed of your fluid flowing through your hydraulic motor in gallons per minute. And then you have speed of your actual spinning revolutions of your pier in RPM, revolution per minute. So flow rate is directly related to the speed of your rotations per minute. So at 20 gallons per minute on this drive head, it will rotate approximately 8.82 revolutions per minute. Vice versa, at approximately 15 revolutions per minute, you'll require 35 gallons per minute to get that speed. So that's how that drive head chart works. Now let's apply this back to our examples and go through to determine what our pressure reading requirement is for a particular torque. So remember from our first example, we determined a torque requirement of 5,600 foot-pounds. So now you're out in the field and you're installing the pier. You've determined your back pressure for that machine is 300 psi. And you're using the RS-12 drive head, the chart I showed in the previous slide. So this 300 psi may or may not be what your specific machine will end up having when you get it, but I'm giving you this as an example. It'll be somewhere in the 50 psi to maybe 500-600 psi range will be your machine back pressure. So the questions I'm asking are what is the differential pressure, and what should the forward pressure gauge be reading on your inline pressure relief? So this is going to have a step-by-step as well. The first step is find the installation torque value on the drive head chart. So our installation torque value is 5,600 foot-pounds. So on the torque chart, 5,600 foot-pounds falls between 5635 and 6069. So between 5202 and 5635. You want to round up to the higher of those two values, the 5635, and read off the corresponding pressure, as that is 1,300 psi. So at 5635, the differential pressure requirement is 1,300 psi. So you now have what that difference between the forward and back pressure gauge is. So now you want to determine what your forward pressure gauge should be reading. So this differential pressure of 1,300 psi is what you'll determine prior to going out to the project. So you now know that you need to reach 1,300 differential psi. So you go out there and you're installing with a 300 psi back pressure and a target of the 1300 differential. You will simply add the differential pressure to the back pressure. So 1300 psi plus 300 psi gives you a forward pressure gauge requirement of 1600 psi. One check is your forward pressure should always be the highest reading when you're going into the ground. Back pressure should always be the lowest reading, and the differential pressure should be in between the two. Let's do another example. So in this example, we go back to the second part of that first set of questions, where we determine the installation torque to be 8,000 foot-pounds. We're now out in the field and our machine is getting 200 psi of back pressure, and we're using the RS12K model drive head. So we need to determine what is the differential pressure and what is the forward pressure gauge reading. So I'm going to give you a second to determine the first step. So the first step is find the installation torque value on the drive head chart. All right, have you found it? It falls in between 7808 and 8677. You want to round up. So from 7808 and 8637, you round up to the 8637. You go to 8637 and read off the corresponding differential pressure, and that is 2000 psi. The third step is to calculate your forward pressure. So to calculate forward pressure, you take your differential pressure of 2000 psi and add the back pressure. Back pressure is 200 psi for this project, or for this specific install. 2000 plus 200 equals 2000 ps. Incorrect. 2200 psi. It's a mistake there. We'll adjust that. So this should be 2200 psi. All right, so that's the end of section 3. We'll be back here shortly to the Zoom call for some Q&A. If you want to go back and review a little bit of this section before attending the Q&A to figure out some additional questions you may want to ask, or write down some notes for the quiz, please do that now, and we'll be back shortly. Thank you.